Hello, welcome to a new video on automorphisms in group theory. First, we see the definition of automorphisms. And an isomorphism from a group G onto itself is called an automorphism. See, an isomorphism from a group G onto itself is called an automorphism. So, when we define an automorphism, we don't want two groups, we want only one group. See some examples. First example, we define an isomorphism from C to C, C1 to C. Phi is defined from C1 to C. It is defined by phi of A plus IB equal to A minus IB. See, A plus IB is a complex number. A plus IB, it's a member of the group of complex numbers. See, with respect to the operation of addition. So phi of A plus IB, but here maps to A minus IB. That's also a complex number. We can show that it's an automorphism. So first we can show that it's an isomorphism because it satisfies all the properties of isomorphism, and then since both groups are same, we can call it an automorphism. And the operation here is addition. Next example, we consider the restriction of phi to the set C star. C here we the function or the isomorphism stated here, that is phi. Phi is the restriction of the isomorphism, which was given, just explained here in the previous example. In the example which is given above. Okay, and that isomorphism is taken, and then its restriction is considered. It's a restriction on the set C star. What is C star? C star of non-zero complex number. See, C star contains only non-zero complex numbers. Of course, here the operation is multiplication. The addition operation cannot be used. That's why we are since we are avoiding that zero, the element zero, we cannot use the addition operation. So here it is clear that the multiplication is the operation. And we define the automorphism using multiplication, with respect to multiplication. And another example, third example is defined on the set R2. R2 is the Euclidean two-dimensional space R2 that contains the paired elements. This group contains the paired elements AB, where A and B are both real numbers, and we define the function phi on AB. It's defined on R2. The function phi is defined on R2, and it maps AB to BA. So phi of AB is mapped to BA. BA is also an element of R2. Then it is clearly an automorphism of the group. So to show that these are automorphisms, first we need to show that they are isomorphism, and after that, automorphism and the proof for automorphism will be it will follow immediately, because automorphism means an isomorphism defined from one group to the same group, because here the same here both groups are same. So when one show that the function is an isomorphism, then the fact that it is an automorphism immediately follows. Here, the operation, the last example in the previous in the example 3. In this example, the operation, what is the operation defined? Here the operation defined is component-wise addition. So with respect to component-wise addition, we can establish that it is an automorphism. Next, okay, that's explained here. How do we add component wise? See, x1, let's take two elements, x1 y1 and x2 y2. Two elements are taken, and then x1 plus x2, y1 plus y2 is the result. X1 y1, x2 y2 is taken, and the result is, when they are added, we get x1 plus x2 and y1 plus y2. Next definition is the inner automorphism induced by. See, we want to define, the inner automorphism induced by the element A in a group G. What's meant by it? The inner automorphism, we can define a special automorphism. It's a special kind of automorphism. It can be given as an example for automorphism too. Okay, the inner automorphism, which is actually defined by a particular element of the group. We take that element equal to A. So let J be a group and A be an element of G. The function, we define a function um, related to the element A. Phi of x, which is defined by okay, we define a function. See, phi a, actually phi a, which is defined by phi a of x is equal to phi a of x equal to a x a inverse. See, this is the function phi. In order to indicate that this function phi is associated with the element, the particular element A. See, it's because we are using this element, this special element, this particularly selected element from the group G to define the function phi. So it should be indexed with the phi. It should be in this phi should be indexed with A and not with x actually. So there's a correction. So phi of A, which is defined by phi A of x, is equal to, so image of x, and we take an arbitrary element, any element of G is taken, that is x. Let x be any element of G. Then phi of x is equal to ax a inverse. We can define ax a inverse, and that is also an element of the same group. Ax a inverse is an element of the same group. Okay, this way we can find the image of every element in the group G under this, particularly under this function defined here with respect to the particular element here. And this kind of automorphism is called the inner automorphism. It is called the inner automorphism induced by, or the automorphism induced by the element A, or the inner automorphism induced by the element A. See another example. The inner automorphism of D4. An example for the inner automorphism is provided here. See, the inner automorphism of D4. In this example, we are discussing inner automorphism of the group D4 induced by the element R90. R90 is the element of D4. So it is induced by our inner automorphism is induced by the element R90. It is given below. Here it is given. You can see that. See, the first, it's a table prepared here. The first column contains all the elements of D4, and the second column contains the effect of the application of or the effect of the inner automorphism, application of the inner automorphism, that is the effect of R90 as described here. R90 is previously, that element is pre-multiplied by R90 and post-multiplied by R90. It's inverse, R90 inverse. It's the element X is post-multiplied by R90 inverse. So in each case of element of the group D4 is the group here, and we want to find the result of the application of R90. So when the element is R0, then we have R90, R0, R90 inverse. We get R0, R90. When then element is R90 itself, then R90, middle part is the same element, R90, then R90 inverse equal to R90 itself. And when R190 is taken, then we get R190. And R2, when R270 is the element, then we get R270. But if we take the element h, then R90H, R90 inverse equal to V. The V is another element, and V equal to V then gives, when V is used, R90V, R90 inverse equal gives us H. And when D is the element, then R90 D, R90 inverse equal to D prime. And when D prime is used, D prime when used at the middle part, then R90 D prime, R90 inverse equal to D. See, when D is used, D prime is the result, and when D prime is used, then D is the result. When H is used, V is the result, and when V is used, then H is the result. That's the result. Okay, that's the effect of the application of R90. So this is this way you can see that every elements are same, but elements here R0 is mapped to R0, R90 is mapped to R90, R190 is mapped to R190, R270 is mapped to R270, H to V, V to H, D to D prime, D prime to D. And these are the effect of the inner automorphism, which is induced using the element R90. Okay, next. Okay, we have a theorem next. In this theorem, see, we are going to show that automorphism of Zn is isomorphic to Un. We consider Zn. Zn is the class of it contains the class of integers modulo n. The classes formed by modulo n, classes of integers modulo n, and we consider the automorphism group of that that group, and Zn is a class. So automorphism group of the group Zn, the operation in defined in the group Zn is addition. Addition is the operation applied, or that is associated with Zn. And then we consider automorphism group of Zn. So automorphism group, automorphism group means automorphism. We consider all automorphisms of all automorphisms of a group, and then we get the automorphism group. So Zn, in order to get automorphism of Zn, we have to consider automorphisms or automorphisms of Zn, and that set is considered, and we can show that it's a group. By itself, it's a group, and that is isomorphic to Un. Here, what we want to show in this result, in this theorem. And okay, this is true for every positive integer n. Okay, how can we prove this? So we know that any automorphism is determined by. In order to show this, we want to recall the fact that every automorphism is determined by the value of alpha 1, which is present in Un. So you should remember that every automorphism is determined by the value of alpha 1, an element of alpha 1. It's an element of Un. So we define T from Zn to Un, and after that we define a mapping T from Zn to Un. It is defined by T of alpha equal to alpha 1. We define it by T of alpha, T alpha equal to alpha 1. And then T is, next we shall show that T is 1 to 1. And after that we will show that T is on to. So first step to show that it is 1 to 1. So suppose alpha and beta be two elements of automorphism of Zn. See here, so or it's T is actually defined from not from Zn to Un. See, it's from automorphism of Zn. That's a correction. So T is defined from automorphism of Zn to Un. So let us take two elements alpha and beta in automorphism of Zn, and then these elements are selected such that alpha 1 equal to beta 1. See, there they are selected. Alpha and beta are two elements of automorphism of Zn such that alpha 1 equal to beta 1. Then we know that alpha k, can be then written as k into alpha 1. Beta of k equal to uh, k into beta 1, because see the elements of Zn are, see, 1 2 3 etc. These are the integers are elements of Zn. So therefore a beta of k equal to k into beta 1, and that therefore that is alpha k equal to beta k, because that's alpha k equal to beta k for all k, and therefore it's because alpha 1 equal to beta 1. We since alpha 1 equal to beta 1, so alpha first you can write alpha 1 equal to beta 1, then you can I can multiply both sides by k, then we get alpha k, k into alpha, k into alpha 1 equal to k into beta 1. Therefore alpha k equal to beta k. Thus we get that alpha k equal to beta k for all k, and so since this is true for all k, alpha equal to beta. Thus we get that alpha equal to beta. So whenever we take two elements of automorphism of Zn, alpha and beta, in automorphism of Zn such that alpha 1 equal to beta 1, then alpha equal to beta we get. So the correction once again I repeat it. There is a correction that T is not defined from Zn to Un. T is defined from automorphism of Zn. So here AUT must be included. So AUT of Zn, T defined from AUT Zn to Un. So let's continue. Next we shall show that it is T is onto. We shall show that T is onto. So for that let us choose an element R of Un, R in Un. Now consider the mapping. Consider the mapping alpha from Zn to, consider the mapping alpha defined from Zn. From alpha defined from Zn. We consider the mapping alpha from Zn to Zn. So that's our automorphism. We are considering an automorphism from Zn to Zn such that alpha of S is equal to R into S, which is defined by, we consider the mapping alpha from Zn to Zn, an automorphism such that alpha of S is equal to, because S are the members of here S is the member of Zn. So alpha of S is equal to R into S mod n, R into S mod n, and where alpha is an automorphism of Zn. Then T alpha equal to, T of alpha equal to alpha 1 equal to R. Then T alpha equal to alpha 1 equal to R. So T is an automorphism. Then we get. So if under this consideration, with respect to this consideration, we get that T alpha equal to alpha 1, that's equal to R. So T is 1 2, and therefore there exists alpha. So thus we can say that alpha is a member of the automorphism group such that T maps alpha to R. So how do we get this? It is we get this because of the facts stated here, and because of this explanation here, alpha of S is equal to RS mod n, and this is true for all S in Zn. Next, T is operation preserving. We shall show that T is operation preserving. For that, let's choose alpha and beta be two elements of automorphism of Zn. Then T of alpha beta equal to, see, directly you can write that it is equal to TB. How do we? By using the definition of T. So alpha beta of 1, we can write alpha beta 1, and that equal to alpha of beta 1. Okay, alpha of beta 1. But that means beta 1 will be then repeating, so alpha of beta 1, but beta 1 will be some integer, some value, some number, some integer number, not an ordinary, not any other number. It's an integer number. So beta, since beta 1 is an integer number, then that can be written as 1 plus 1 plus. It can be written as 1 plus 1 plus is positive integer number. So 1 plus 1 plus 1 plus, how many times? Beta 1 times you need to write. So alpha of 1 plus 1 plus 1 plus that much time, and then we can split it using the property of alpha, automorphism. So alpha 1 plus alpha 1 plus alpha 1, that you can write alpha 1. Then how many times it will be there? Since there are 1 beta 1 times, then we have alpha 1 also beta 1 time, beta of 1 time, and therefore the value can be yeah, it can be shortened, so it can be simplified to write the alpha 1 into beta 1. So it's because there are alpha 1 terms. So, yeah, there are beta 1 terms of alpha 1. Alpha 1 into beta 1 is the answer. But alpha 1 equal to T alpha and beta 1 equal to T beta. So that's written. And this shows that uh, T is T is what? T is operation preserving. Thus, we have shown for three things: T is one to one, T is on to, and T is operation preserving. Okay, therefore, what we can conclude, and also T is T. It is defined from automorphism to UN. T is here defined. Where is it defined? We define T from automorphism of Zn, automorphism of Zn, ut of Zn to Un. T is defined, and that T is one to one, on to, and operation preserving. That means it is uh, it's an isomorphism. So T is an isomorphism. As T is an isomorphism, therefore automorphism of Zn is isomorphic to Un. Okay. Okay, that's all. Yeah, thank you for watching this video.